Hey Finxters, today I want to talk about logistic regression in Scikit-learn as compared with Statsmodels. Both the Scikit-learn and the Statsmodels package have logistic regression, but what you see in Scikit-learn is done from a machine learning perspective, whereas Statsmodels is from a statistics perspective. And so we really need to understand the difference between statistics and machine learning. Statistics is the study of making mathematically valid inferences about a population based on sample data. So it can answer questions like, what is the evidence that X is related to Y? Given I have some sample data, what is the evidence that overall X is related to Y in the wider population? So for example, I've got boys and girls in my class and I want to know, okay, I see that on average boys in this class have a little bit higher height than girls. Is that true in general for all boys and girls, right? That would be a statistics question. Whereas machine learning has the goal of optimizing predictive accuracy rather than inference. And so machine learning is trying to answer the question, given X, what should the computer predict for Y? So this is a boy, what height should I assume that that boy has most likely, right? That is more of a machine learning perspective. It'll make more sense with the example below when I'll use the same data for a Statsmodels logistic regression and a Scikit-learn logistic regression. So now let's create our data that we're going to use with Statsmodels and Scikit-learn. And I'm going to use NumPy to do that, creating an array of random values that are going to follow the normal distribution. And it's going to be 500 rows and 3 columns. And I'm going to click run here. And then if I go back up, I can add another cell and just show the first couple rows here, maybe the first 5 rows actually. Click run. And so now we see 5 rows of the data. And I'm going to use these values, these X values, to create my Y value. However, I don't want to have actually all of this data to train my model. I'm going to get rid of some of the data because normally when you're creating a model, you don't actually have all of the data to create the perfect prediction. I'm going to delete this first column here and add 2 more columns that are correlated with the second and third column. So I'm going to run this 20, and that is going to do my delete. And let's take a look at X1. Just copy this. So there are the first 5 rows of X1, taking these 2 columns. And then I create X2 with X1 plus some random variation. So that's going to make X1 and X2 correlated. Then I'm going in the next step, concatenate X1 and X2 so that I have one array. I'm going to run this and then take the first 5 rows. And so here and then here. So now this is the data that I'm going to be using to train my model. Now in this step, I'm going to calculate the probability, but I'm going to use this original data, the data before I dropped the column and added 2 more columns to create a probability. And this is using the logistic function, which is always going to give me values between 0 and 1. You can look at the curve of the logistic function, but in order to create sort of valid probabilities, you don't want ones that are 2, 5, 10. You just want numbers between 0 and 1, and that represents a probability. And then I'm going to set the Y value as true whenever the probability is above 1/2. And then I use NumPy mean to figure out the percent of cases that are above 1/2, and it comes out to 0.498. So half the cases are true, and the other half about are false. And so now I can look at what my outcome is. Again, take the first 5 rows or so. You see true, false, false, right? So I'm going to use this data to predict this. Is it true or false? And now I'm going to divide my data into a training and a test set. So I'm going to use the first 50 rows as my training set and the remaining rows as my test set. The neat thing about doing it this way, creating our own data, is that if you wanted to add more columns of predictors or change the correlation or have missing data or whatever, you could do all of that. And you actually know the exact relationship between the data you created and Y, the outcome variable. And so you're sort of creating the answer and then seeing how close the logistic regression model can come to it, right? So you can kind of play around with the data when you're creating it yourself. And so now we're going to move to using Scikit-learn to do the logistic regression. And we do use this import statement, and then we do the fit, and we print out the coefficients, and then we use the score method, and that's going to tell us how accurate we are on the training data and then on the testing data. One thing to note is that by default, and we're using the default settings here to start with, logistic regression in Scikit-learn applies regularization. Regularization is a way of penalizing larger values of the coefficients in the logistic regression model. And so instead of doing a pure logistic regression, we're actually doing a penalized logistic regression where we are applying a penalty to the magnitude of the coefficients. And that is balanced against the accuracy on the training data. The reason we want to do that is that we want to avoid overfitting. Overfitting is where our model fits well on the training data, but doesn't generalize to the test data. And by reducing the value of the coefficients, that tends to help us to avoid overfitting. So in this first example, if I look at my train accuracy, it's 0.8, whereas my test accuracy is 0.82. It's actually slightly better on the test data than on the training data. So it's looking at the new data that it hasn't been trained on and actually getting a higher accuracy score, which means that I'm not having a problem with overfitting here. Now, if I scroll down, I've done another example where I set the penalty equal to none, and that turns off the regularization. And so in this second example, we see now that the training accuracy is 0.82, but the testing accuracy is 0.78. So we're not doing as well when we're using new data that the model hasn't been trained on. And that's because we've overfit the data, probably due to the fact that we've turned off the regularization. And so we're trying to optimize our predictive accuracy on the training data, and we don't generalize so well when we move to the test data. So we've done the logistic with the default settings, and then we've done it with penalty equal to none, and so that turns off regularization. Now if we want to increase the regularization, there's a parameter C, which we can set to be 0.1, and that's going to increase the regularization. The default is for C to be equal to 1, and by using a smaller value, we actually increase the regularization. And so if we look at these coefficients, and we compare them to the coefficients up here, we'll see that these down here are all smaller, lower magnitude than what we had up here, because now we're using stronger regularization. And so that's going to tend to smooth out these coefficients and reduce their magnitude. And so by adjusting this parameter C, we can either increase or decrease the regularization. So we can use the default settings. We can set the penalty to none to turn off regularization, or we can choose a particular value for the regularization coefficient. But this just raises the question, well, what's the best so that I'll have the most accurate value on my training data? And there's no general answer to that question. I can see if I make C very small that I end up reducing the values of the coefficients and ending up with actually a worse training accuracy. So that's where I've underfit the data, but it's not clear in general what the best value is for C. So I have to kind of play around with my particular data and figure out the optimal value for the regularization. There's a more systematic approach, which is to use this grid search CV. And the grid search portion of this means that it's going to search through a table of parameters that you give it. And so I'm giving it all of these possible values for C and all of these possible values for this other parameter called solver. And it's going to go through the different combinations that I supply and try them to see which works the best. Then the CV portion of grid search CV means it's going to do something called cross-validation. And that's where the training data is actually segmented into a portion that's used to train the model and then a portion that's used to validate the model. And that's done repeatedly. And then we see which values for C and solver work best on the validation segments as we go through these different iterations. And so this is a way to use the training data to basically select the best values for C and solver by iteratively looking through the different combinations of C and solver and going through different iterations, segmenting the training data into a training portion and a validation portion, and seeing what works best to create the best estimator overall. And so we can do this with just a few lines of Python code. Here I'm giving the grid of parameters, right, this dictionary object, and here I'm fitting the model using, instead of logistic, it's actually the grid search CV. I tell it the algorithm and the parameters. And now I'm fitting, and then I'm printing out the best estimator. And so it tells me that after it does all this, it knows that the best estimator for the logistic is to set C to 0.1 and set the solver to Newton CG. And so now I've chosen my best value for C, and that's the end, and I can kind of print out the training and test accuracy for that best estimator. Now let's take a look at logistic regression with Statsmodels. A couple of important differences here. We see that we have to use this add constant method in order to include an intercept in our logistic regression model. That's included by default with Scikit-learn, but with Statsmodels we have to use this add constant method, otherwise we won't have an intercept in the model. Also, by default, Statsmodels does not use any regularization, so it's as though we have penalty equal to none with Scikit-learn. That's by default with Statsmodels. However, once we fit the model, we can print out the parameters like this in much the same way that we did with Scikit-learn and see what our coefficients are, like that. Also, this summary method gives us a table that should be very familiar to those who've used R or SAS. It gives us statistical measures that tell us whether we have a statistically significant relationship between our predictors, x1, x2, x3, x4, as well as our intercept, and our outcome variable, our y variable. And so this is useful if we're coming from a statistics perspective and we want to know, is there a statistically significant relationship between our predictors and our outcome variable or our target variable? And so here we see all of our p-values are actually below 0.05, which is interesting because we know we created the data ourselves, and actually the x1 and x2 should be very predictive of whether y is true or false. The reason they're coming out as above 0.05 is because we have a lot of collinearity and a relatively small data set. So if I go down here, now I'm training with just the first two predictors, x1 and x2, and I've left out x3 and x4. And now I get p-values that are below 0.05 now that I've removed x3 and x4. This statistical summary table is not available in Scikit-learn, and this is a lot of the reason why people would want to use Statsmodels instead of Scikit-learn if they're trying to answer the statistical question about whether a relationship exists between x1 and x2 and y. Then the way to do that is with Statsmodels rather than Scikit-learn. Now in the last step, I'm going to summarize the results of all of these methods, and we can see what our training accuracy and our test accuracy was, and we see that the no penalty model did very poorly, as did the model that we used with Statsmodels that included all of the predictor variables. Those both had a 0.76 accuracy, whereas the other models had higher accuracy. We did well with the bigger penalty, and we did well with the grid search. There's some sort of random variation, so even if we use the best method, we won't necessarily get the best result every time. But that's a sort of summary table. And now if we pull back and think, well, what is the reason to use Scikit-learn and Statsmodels, and how do they compare? The big differences are that Scikit-learn uses regularization. It has a really nice tool for choosing the best regularization parameter with a grid search CV. It has a very easy way to get accuracy and other score measures. It is different from R and SAS in that it doesn't offer some of the same statistical measures. Statsmodels doesn't have as convenient a method for choosing the regularization coefficient. It doesn't have the same ability to, but it does print a really nice summary statistical table, and it does feel very familiar to people who've used R or SAS. So that's sort of a summary of the differences. One is trying to optimize predictive accuracy, that's Scikit-learn, whereas Statsmodels comes from a statistical perspective and gives p-values and confidence intervals.